This is lesson 9 in the thermal physics topic on the Boltzmann constant. These are the things we're going to be doing today, some of the equations, and there will be a derivation that you are expected to know from this. I'll let you know when we get to that. So first off, we're going to do the second equation of states of an ideal gas. The first equation of states was this one. Pressure times volume equals the number of moles times the molar gas constant times the temperature, which must be in Kelvin. And what we're going to do is we're going to introduce a new constant here. It's called K. K is the Boltzmann constant, named after a scientist called Boltzmann. And K is just defined as being R divided by Na. R being the molar gas constant, which is about 8.31. It's given to you in your formula booklets. And Na being Avogadro's number, the number of molecules in 1 mole of a substance. So this is 8.31. This is 6.02 times 10 to the 23. We're going to rearrange this to make it as R equals. So R equals would be K times Na. And we're going to substitute that into there. And that gives us PV equals N times NaKT. What we can see here is we've got number of moles times Avogadro's number. That is just the number of particles we've got, or the number of molecules. So this gives us our second equation of state for an ideal gas. It's pressure times volume equals the number of molecules times the Boltzmann constant times temperature. You can see these two equations are very similar. This one is just number of moles and the molar gas constant. This one is the number of molecules and the Boltzmann constant. Can you think of what the value for K would be based on how we defined it and what the units of it would be? Well, we would get Boltzmann constant being equal to 1.38 times 10 to the minus 23 joules per Kelvin. A question to try this out is this one. Just pause the video and give it a go. Okay, so this is me working through it. We've got our new equation of state of an ideal gas. We want to work out the number of molecules, so we're going to rearrange it to get N equals. So we get N equals PV over KT. We're going to substitute in our values. We put pressure and volume. We've got our value for K and our value for temperature, which must be in Kelvin. Here it's in degrees Celsius. And we get 3.3 times 10 to the power 29. So 3.3 times 10 to the power 29. And here to work out the number of moles, we would just divide that by Avogadro's number. And we would get 5.4 times 10 to the power 5. So next what we're going to do is we're going to now calculate the root mean squared speed of the gas particles from the temperature. So we can actually calculate roughly how fast our particles are moving simply based on the temperature. And this is a derivation that you're going to be expected to know. So make sure you write this all down in your notes. This is the derivation you will be expected to know. So we're going to start off with this equation. PV equals a third NM mean square speed. This is one we did last week. This is the number of molecules, this is the mass of a single molecule, and this is the mean square speed. It's the square of the root mean square speed. And then we've also got this equation we saw today, PV equals NKT. We can see that on both sides of the equation is PV, so these two sides, the right-hand sides, will be equal to each other. So we can say that a third NM mean square speed equals NKT. I've got an N on both sides, so I can cancel both those N's out, and that gives me a third M mean squared speed equals KT. And what I can do here, you might notice this looks pretty similar to the equation for kinetic energy. It's not quite because we've got this third here. But what I can do is a nice little mathematical trick. And I'm going to say that a third M mean squared speed is equal to 2/3 times a half mc squared. The reason I do that nice little trick is because now you can see here I've got this half mc squared. That's basically the kinetic energy of a single molecule. So this is a nice way to make this as this. So this bit here is the same as this bit here. So I'm going to substitute that in for that, and I would get 2/3 times a half mc squared equals KT. And then I'm going to move this 2/3 over to the other side by inversing it. So I get a half mc squared bar equals 3.5 KT. So here I can see that the kinetic energy of a single molecule is equal to 3/2 times K times the temperature. So what you can do simply by measuring the temperature of your gas, that tells you what the kinetic energy of the molecules are, the average kinetic energy. That therefore means that the kinetic energy of a molecule is directly proportional to its temperature, because M is just the constant and K is just the constant. The two variables being T and the speed, which will affect the kinetic energy. Let's try this now in a question. So here we've got the average mass of an air molecule being 4.8 times 10 to the minus 26 kilograms. What is the mean square speed of an air molecule at 750 Kelvin? Okay, so we've got mass, we've got temperature. This is the equation we just had. And the question is asking us for the mean square speed. That is this term here. I don't have to square root anything there because there's no root mean square speed. It's just asking me for the mean square speed. So I just need to get this as c squared bar equals. So I'm going to rearrange it and I would get this. And then I'm going to stick in my values. I've got 3, I've got k, which is 1.38 times 10 to the minus 23. It's given in your formula booklet. Times T, temperature. It's nice and already in Kelvin for me, which is very kind of them. And I've got M, which is 4.8 times 10 to the minus 26. Stick in all of your values, and you should get an answer. And your answer to the nearest two sig figs should be C, 6.5 times 10 to the power of 5. So, thinking about internal energy now. Internal energy was something we looked at in the very first lesson. Building upon this equation, and looking at the definition for internal energy was defined as the sum of the kinetic energy of all the particles plus the sum of potential energy of all the particles. Now, when we defined an ideal gas, so this is for an ideal gas now, when we defined an ideal gas, we said that there was no attraction between the molecules. The gases are so far apart that they're very rarely interacting, so we can say that there's no electrostatic attraction between the molecules, and if there's no attraction, there'll be no potential energy. So in fact, for an ideal gas, the internal energy of it is just the sum of the kinetic energy of the particles. That means that this term here defines the kinetic energy of a single particle. So if we have got the kinetic energy of all the particles, we've got the total internal energy. So E, the energy of a single molecule, the kinetic energy, is 3 over 2 kT. And this is the energy per atom or per molecule. And then to get that as the total internal energy for the whole gas, we would just times it by the number of molecules there are, N. And that would be the total energy of the gas, the total internal energy. And that is because the only energy that a gas will have will be the kinetic energy of the particles. There are no potential energy of the particles. So using that now, let's try that in a question. Pause it and try the question now. So what is the internal energy of 2.4 moles of an ideal gas with such a temperature of 15 degrees Celsius? Well, I've got that equation, that's what it's given to you. What I'm going to do, I want to work out this side here. So I don't need to know any of these values because this is just energy and that's all I'm looking for. So I just need to use the values on this side, 3 over 2 times K times T. I need to make sure I change T into Kelvin, so I need to add 273 to that. And then I'm going to do this operation over here, 3 over 2 times K times T. And I should get 5.96 times 10 to the minus 21 joules. Be careful though, that is not a final answer. You might be tempted there to just select A. That is not the final answer. That is the energy of a single molecule. But we've got 2.4 moles. So what I now have to do is I have to times that by the number of molecules I have. So I need to do 2.4 times 6.02 times 10 to the power of 23 times the energy per molecule, and I'll get the total energy, 8.6 times 10 to the power of 3 joules. What we notice when we've got a gas and it's made up of a mixture of different molecules, for example, air has got helium in it, it's got oxygen in it, it's got carbon dioxide in it, all those molecules are at the same temperature. The air is at the certain temperature, so all the molecules are at the same temperature, but they'll have different speeds. And that is because of this equation here. We can see that if we rearrange this to get into root mean square speed equals, then we would get this. We can see that for the same temperature, if there is a larger mass, it will have a lower root mean square speed. If the mass is lighter, it's a smaller mass, it will have a higher root mean square speed. So helium, which is much lighter than oxygen and carbon dioxide, will be moving much more quickly, even though they are all at the same temperature.